Okay, so time to get going. So here's where we were last time. We were talking about double integrals. I want to remind you all of the kind of the strategic diagram, what are the objects in play and how do they relate to each other. We started off by considering the question of volume. And I answered the volume question by kind of taking a single variable calculus approach. We sliced and then found that our cross-sectional areas were integrals. So we had an integral inside of an integral, thus an iterated integral, which we can compute with the fundamental theorem. So our very first thing to do was this. Okay, but this came with some attached, asterisks and problems. In particular, you can't make a claim that mass is somehow automatically, obviously equal to a volume. You just can't, right? They're totally different things. It's not at all clear that these should relate. So you can't. That is not a valid connection on this diagram of connections. You also can't take an iterated integral approach to understanding, say, for example, mass. Because, sloppily stated, the units don't work out. You find yourself multiplying mass per unit area times length, which isn't, that's a mismatch. It just doesn't, I guess you could call it mass per unit width, but what is that? Is that something that we have an intuition for? Do we know that we can add up little pieces of whatever that is and make claims about it? Not clear, right? So this is also not really on the table. And so, interesting though perhaps this volume computation may have been, it's a dead end. Right? And that's not good, right? Because what we really want to know, what non-mathematicians really want to know is, how do I apply this? How do I compute mass and work and economic value and populations and many bazillions of other applications I haven't listed there. So we're kind of without luck at the moment. Enter the double integral. Right? And it's a different definition. It's a Riemann sum. What I like to call chop it up, add it up. We take a question that happens over a domain, whatever the question is. Let's be deliberately non-specific about what the application is. If there is some quantity that's distributed across an area, we can chop up the area into little pieces. We can answer the question individually on the little pieces, and then we add up over all of those little pieces. It's morally identical to what we do for single variable integrals. It's just area instead of an interval. So it's very much a Riemann sum, like we saw in single variable calculus. So anyway, we compute this double integral. The very first application we see of it is that we can compute volume with it, and then we think to ourselves, wait a minute, we already computed volume with iterated integrals. That must mean that double integrals and iterated integrals are the same. And now we're kind of in business, because this limited diagram that we had previously, we now have connected to something which connects to these applications. Right? In some sense, the whole point of double integrals and Riemann sums is so that we can connect applications to something that we can then do something with. And in particular, I can rewrite the double integral as an iterated integral, and I can compute iterated integrals with the fundamental theorem of calculus. So this is our three-step process. This is, if you're going to make an argument using double integrals to compute something, these are the three steps. Pausing real quick. Does everybody remember? Is this? Anybody have any questions? Is everybody happy with this? Okay. Cool. Let's do one. By the way, just as an FYI for the course, I've said it a million times. I'll probably say it another million over the course of the rest of the semester. But it's not a course about answers; it's a course about reasoning, right, and arguments. So, because there really is a three-step process here, all three of these steps are important, right? In the sense that you can't do applications without double integrals; they're essential to connect to applications. And yet you can't compute the double integrals directly. We need iterated integrals to be able to compute. And of course, in order to be able to connect these, I need to know that double integrals and iterated integrals are the same. We really need all steps as part of the argument itself. And again, since that's what this course is about, you got to give me all three of those steps. And it's nothing to worry about. It's very streamlined, but nevertheless, streamlined though it is, I do need to see all three of those steps. So here we go. We're going to compute here the amount of mass distributed across an area, specifically this rectangular sheet right here, and specifically the mass is distributed in such a way that the density is given by some function. Let's not worry about what that function is. That's just really not going to come up until the very, very end where we would compute, and we already know how to do that. Okay, so there's the question. Step 1. In green on this diagram here, I need to take my application and figure out how to write that as a double integral. Okay, well, total mass that I want to compute, chop it up, add it up. Oh, yeah, question.
Sorry, I just want to, could you repeat what the FTC stand for?
Fundamental thermocalculus.
Oh.
Yeah, sorry. Yeah. Okay, so mass is what I like to call an accumulating quantity. If you chop it up into little pieces, the whole is the sum of the parts. That's how mass works, right? I mean, is that good news or bad news? I don't know, but it is what it is. And then, by the way, of course, each little piece of mass is density times area. That's what we mean when we say that mass is distributed across an area. And mass is density times size is, that's kind of the definition of density, you might say. And then you notice, oh my gosh, look at this. This is exactly a Riemann sum. Exactly a Riemann sum. And so Riemann sums, of course, being the definition of a double integral. There you go. There's your double integral. All right. Now, everybody with me so far on this argument? Is that cool? All right. Before I go on to the next step, let me introduce a notation, shorthand. It's very convenient. It's extremely common. And look, it's just notation, so let's not worry about it. I don't want to get too upset about the particulars and the strictness here. But because we will eventually kind of be turning delta x, delta y into dA, right? That's how we write double integrals. Again, dA is really just a shorthand for delta x, delta y. And likewise, in some sense, this is going to turn into that, right? The case could be made that I could use those convenient notations as I develop the Riemann sum. It's arguably the same exact thing. So, in practice, people don't usually write like this. In practice, it's just a little easier to say mass is, let me do it like this. Mass is sum of a bunch of little pieces of mass. We just write double integral dm. And you see where we're going with this, right? I mean, no, there is no M axis. M is not area, right? I have not defined a Riemann sum with M in it, and yet I think it's pretty believable that that is a pretty clear representation of that, which is fine. Okay, and then likewise on down the line. So in practice, this is typically how we will get to the double integral. You're very welcome to use this notation. In fact, I encourage it strongly. Okay. All right, next. We've got ourselves a double integral. We don't have any immediate tools for computing double integrals. So we go back up to the diagram. What does it say here? The diagram says, okay, the next step is to rewrite the double integral as an iterated integral. And there's hardly anything to show there, but this is the corresponding double integral. And notice the range of values of x in our rectangle are the x bounds. And the range of values of y on our rectangle over which we're doing this summation is our y bounds. So, I mean, that's just an iterated, I mean, it's kind of an immediate thing to write down. Hardly anything happens there. But I do have to do it because I need to be able to compute the double integral, and I can't, but I can compute iterated integrals. Okay, and then last step, once I've got an iterated integral, then I can compute that with the fundamental theorem of calculus. I'm not going to crank that out, but the point is and we've done these before, right? And it's just a matter of working from the inside out. Don't forget which variable is a variable, which variable is a constant, at which point in the calculation. Got to be careful about that. Other than that, it's just single variable calculus. So notice the 3-step process, and I'm coming back up to here. We've done all 3 of the steps. In practice, as you're writing these down on exams and stuff, you don't have to write as much as I did in this example. In this example, I wanted to flesh it out extremely broadly, just for visibility purposes. Here's a reasonable representation of what you should actually write on your exams. Mass is a double integral, which is an iterated integral. And then you compute with the fundamental theorem of calculus. Obviously, you have to write out the details for that. So notice, all I'm asking in some sense is just don't do this. Just don't skip directly from mass to an iterated integral. That's effectively doing this, which again, we've already agreed, that does not make sense as an argument. It doesn't hold water. It's not a valid reasoning, argument of reasoning. So the upshot, all you have to do to avoid what I'm asking you to not do is just don't forget to represent the double integral step. It's one little thing to write down. That's a doff of the cap to the necessity of the double integral in the argument itself. Right? Again, very important. And then proceed. Calculate as you would sort of like to, efficiency-wise. All right, is everybody happy with that? Yeah.
Just a quick question.
Yeah.
Is it reasonable to conjecture that because this is a 2-dimensional space?
Yep.
We're using double integral.
Yes.
So if it's an n-dimensional space, should I use like integral signs?
We were eventually going to define something called a triple integral. And yes, it's going to use 3 integral signs, but we haven't defined that yet, and we need to write some stuff down. There's things that have to get established before we do. I'm not going to give anybody in this class any questions beyond 3 dimensions in terms of integrals. I'm not going to make you do the 6-dimensional integrals that I had to do when I was taking various, blah, blah, blah. It's not that you couldn't probably speculate reasonably. What you speculate would probably be right. It's fine, right? But it's not something I want to spend class time on, and it's not something I could then reasonably demand of students. But yeah, pretty much exactly what you think, probably. Yeah. Good. Okay. So this double integral notation, this convenient shorthand, it's also nice when you're developing Riemann sums that are a little bit more complicated, a little bit more involved. So here's an example of that. Suppose you are building a wall. I thought of this problem when we were building our house like 15 years ago, and there's a stone sort of facade, and at one point and so they have all these stones, sitting on the ground, and they're going to be building this wall, and it occurred to me that is a lot of stones to have to pick up. I mean, the wall is up there, and that's a lot of weightlifting. How much work do they have to do to build this wall? Right? So let's calculate, and I added some silly parameters just to make it mathematically more interesting. But so roughly speaking, the wall is defined by this rectangle. Y is up, X is across. And this is the silly part. I'm going to speculate that the density, namely how much do the stones weigh per unit area coverage on the wall? I made up a random function here. This is not representative of my house, where things were mostly uniform. But that's just to keep it mathematically interesting. So how much work does it take to build this wall? Ignoring the much more that obviously goes in, but just in terms of the lifting of the stones, how much work is that? Okay, so I argue as follows. First, work is an accumulating quantity. If I were to break up this task into a bunch of little small micro tasks, the total amount of work is the sum of the amount of work in the micro tasks. I think that's pretty believable. Yeah? Everybody all right with that? How much work does it take to accomplish a microtask? I'm going to define my microtask to be associated to a particular stone, and I have to pick up that stone. I didn't do it. Those guys had to pick up the stones and lift them that high. And if you know weight, which is force, right, and the distance that you have to lift it, well, work is equal to force times distance. Is that cool? And notice I'm using this integral shorthand. I'm drawing it, writing it as if it's a differential, which, if I were to write out a Riemann sum, this would be a differential quantity. The small amount of work that it takes to perform the microtask. There's a new differential down here, which is how much does that little differential amount of brick weigh? Stone, brick, whatever. Right? It's a differential quantity of force. It's a very streamlined way to write this down to that point, is just using this integral shorthand. And we keep going. How much does this piece of stone weigh? Well, weight is density times size. And in this case, the density, this density here is to be understood as weight per unit area of coverage on the wall. So weight per unit area. And so weight is equal to weight per unit area times area. Again, the units fit. Makes sense. Now, notice we have ourselves a double integral. So you might call this development here, this is my sort of phase one, right? This is the part one. Oh, my colors are all confused at this point. But, my first step, turning my application into a double integral, is this part right here, and notice that the integral shorthand is convenient for that. Does everybody buy it? Okay. The remainder of the question is pretty straightforward, but let's walk through some of it anyway. Turning a double integral into an iterated integral. Well, arbitrarily, let's do my slicing in this order. Doesn't matter. It's a rectangle. What's the range of values of x? Well, right there. The range of values of x on the rectangle. 0 to 10. What is the range of values of y? Well, again, right there, and 0 to 6. What is my density here? Oh, well, there it is. Formula, given, density, boom. Right, and now we have an iterated integral, literally an iterated integral. Now it's pretty much single variable calculus, and so, go crazy, and bam, answer. Everybody fine? Okay. All right. Okay, so now we're going to entertain the big next question, the big asterisk on everything that we've done so far. We've been trying to answer questions when some quantity like mass is distributed over an area. We've developed Riemann sums and iterated integrals and all that stuff, but we've been looking exclusively at rectangles. World's easiest area. What if it's not a rectangle? In other words, what about real life, where hardly anything's a rectangle, right? So, all right, well, we're going to kind of start off at 0 again and ask a volume question. Here you go. Here we're looking at a surface. Right? I have a graph, some surface here, and I want to compute the amount of volume, blah, 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 but specifically now I want the volume sitting over this highly non-rectangular domain, right? So this is not a rectangle. Everybody with me? So can we proceed? Does this still work? And the answer is, yeah, this is fine. It's really not a problem. There's one little minor tweak. We're going to have to tweak one thing. But structure of the argument, no problem. Is this volume the sum of the slices of volume? Yeah, of course it is. Volume's an accumulating quantity. The whole is the sum of the parts. Sure. Right? is one of these slices, oh, come here, is one of these slices area times thickness still? Yeah, that's no problem. Can I compute that cross-sectional area? Cross-sectional area here. Can I compute that cross-sectional area as an integral? Is this an area under a curve? Yeah, totally. It's an area under a curve. I compute areas under curves with integrals in that direction. No problem. Iterated integral. It's all fine. No problem. Here's the asterisk. One little thing changes, and that is these bounds. You'll notice that I've written them here as being functions of y. So let's think through, why would it be that these bounds would be functions of y? Well, let's just look and see where is my lower bound. In this picture, my lower bound comes from, well, wherever that point is. Let me zoom so we can see better. That point, I think it's a pretty clear case that as this y varies, in whichever direction it goes, well, this point is going to move along that curve, and we're going to get, therefore, different values of x. And so, for example, over here, I get a different value of x for a different value of y. And then, further along the curve, yes, still different values of x for that value of y. So the location, the x value here that is my lower bound for my x integral, it depends on which y slice you're looking at. That's all there is to it. Is that cool? But other than that, other than the fact that these bounds are now no longer constants, they are now functions. Let me point out further. They are functions of, you'll notice, they're functions of the outside variable. Inside bounds are functions of the outside variable. That's always the case. Whether you're doing dx, dy, dy, dx, dp, dq, whatever. Inside bounds are always functions of the outside variable. Other than that, everything's exactly the same. Go crazy, knock yourself out. Okay. So that's really good news. We've now extended the reach of this idea of a double integral, not just previously defined only on rectangles. Now we've got a way to think about it over any kind of domain. And then here's some even better news. Now, I drew this picture here, and it was on this picture that I made the argument about why am I in gray? About why these bounds would be functions. But do you notice, now that we've established that the volume question, was addressed by the same tool, notice I didn't need the z-axis here at all. In order to figure out what these bounds are, height does not play a role in that question. These inner bounds are determined only based on what's going on these curves. These curves being entirely contained within the xy plane. And this is a huge observation because three-dimensional pictures are hard to draw. Why should I be drawing a very hard to draw three-dimensional picture if I really only need the two-dimensional picture? Right? So, nice observation. I can throw away that picture, look instead at just the domain, and looking at just the domain, I can infer my bounds. And so, for example, again, for a given value of y, I can look at this point to find my lower bound. I can look at this point to find my upper bound. For the x integral, going across there, right, computing the inside integral as I should, x goes from a to b. And it's just easier to see there than it is to see here. So, again, good news. So here's the big strategy. Notice that these bounds, right, given the value of y that we're looking at, those bounds define those points lie on certain curves those curves, of course, have equations, and then we can then solve those equations and actually find the bounds that we're looking for. So this is the process that I want you all to always be thinking in terms of when you're finding your inner bounds. Identify what is the relevant point. Right? First, find the relevant point on the picture. The picture tells all. Oh, and by the way, again, you gotta have a picture. It's really important. Don't try to do this kind of thing without a picture. For one thing, you're much more likely to be either unable to think it through or to think it through incorrectly. Much more likely. Second of all, again, a huge point. I know I say this a lot. It's all about the reasoning. I need to be able to see your reasoning, and the picture is unavoidably a huge part of the reasoning. This is a very geometrically oriented class. It's intrinsic to the material. You gotta, I mean, my gosh, it's hard to even imagine how you could make a clear exposition of the reasoning without having a picture. That's part of that. So make sure to draw your picture. Okay, so I identify the relevant point on the picture. Notice what curve that point is always on for all values of y in this case. Find the equation of that curve and then, again, solve in the equation to find the bounds that you're looking for. That's the process. Let's do one. Suppose we want to do this integral right here. This is an integral defined on, you'll notice, a triangle with certain vertices given. And I've got a double integral given to me. I want to turn this double integral into an iterated integral. I want to pause real quick and scroll back to my diagram. How come I haven't told you what application we're working on here? Let me go to... Don't I need to know what application we're working on? Don't I have to, justify the double integral first? If the question were to compute the answer to an application. Right now, I just want to focus on just this part. On an exam question, if the question is compute the population, blah, 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 then yes, you got to develop your Riemann sum. But we are given the Riemann sum, and the question is asking us only to find the associated iterated integral. So this is purely step 2, phase 2, if you will. That's all we have to do in this question. Is that okay? Is everybody happy with that? So let's not worry about, I don't really care what we're actually computing. The double integral is already given. Okay, so double integral given. Got a domain. The domain is a triangle. How do we proceed here? Arbitrarily, doesn't matter. I'm going to do my dx on the outside. So I need to think of the range of values of x as I slice up this triangle. Notice that we start where x is equal to 0, and we end when x is equal to 1. I didn't even really have to do any work to find these values of x. I mean, I guess you could say that because the starting value of x is at that point, I can look at the x-coordinate of that point. Similarly, I could argue that the ending value of x is the x-coordinate of that point. Right? But again, once you have your picture drawn and labeled, these things are pretty much probably already clear from the picture. Okay. Sometimes you have to do a little algebra. We can see many of those examples. Okay, so x goes from 0 to 1. Is that all right? Okay. Now, we're going to focus now on a particular x slice. For that given value of x. Looking now just at that value of x, we ask the next question, what are my inner bounds? And this is, again, where you have to, you got to be careful about this. What are my y bounds? My y bounds, the lower bound is defined by this point, which is on this curve, now let's think about that curve. Thank you. Picture, by the way. Good thing we have a picture. I can see exactly what curve the defining point is on. And looking at the picture, I see, that's the x-axis. That's no problem. That has this equation. Yeah? Everybody good? Okay, and then, last step, in order to find the bound itself, in order to find this bound, I have to solve for y in this equation. Now, a lot of people gloss over this part too quickly. In this case, it's trivial. It's easy to solve for y because it's already solved for, right? But anyway, I want to still recognize that technically we are solving for y, however trivial it is, and that gives me this lower bound, which is 0. Everybody happy? All right, now let's go to the upper bound. Let's see. Here, why don't I do that? Okay, so the upper bound for y. There's the point. It's on this curve. Thank you, picture. I'm going to have to figure out the equation of that curve. It's not given. It's easy, but it's not given. So there is a process here. On an exam, you don't have to. For something this easy, if it's just that painfully obvious, I mean, this line that I'm interested in contains these 2 points. It's just screamingly clear that the equation there is this equation, right? Like that, right? But anyway, got to write that down. And then again, now we have to solve. Let's see here, color choices. I'll use this color. I need to solve for y in this equation, right? I'm trying to find y bounds, so I have to solve for y. So solving for y. Oh, again, lucky break, it's already solved for. It's just x. And so x is my upper bound, defined by that point. How we doing? Is everybody happy? Okay. You might want to worry momentarily about the fact that, hey, wait a minute, I thought bounds were supposed to be constants. How come we've got a variable in here? I'm concerned about the fact that this bound at a glance doesn't appear to be a constant. Don't forget, though, it is a constant because we are looking only at this value of x. Said differently, the outside variable is a constant for the purposes of the inside integral, and so even though it doesn't look like it, that x actually is a constant, so it's all fine. Yeah? Cool. That's the process. Okay, we're going to just see several more examples now. I'm going to start moving faster, just because we've been down this road a couple times already. Let's slice it the other direction. Range of values of y. Well, y starts at 0. Y ends at 1. 0 to 1. Cool? Let's fix a value of y. Look at that one y slice. On that y slice, what's the range of values of my inside variable x? Okay, well, the lower bound, that point, that curve, that equation. Slow down. It's tempting to move too quickly and say, so therefore x. Right? But no. It's not going to be, the inner bound is not x. We have to solve for the variable that we're looking for. I need to solve for x. I need to write x as an expression. Specifically as a constant, keeping in mind that y is a constant, I'm allowed to use y as a constant, and so the answer for what x is, solving for x, it's y. So y is this lower bound for the x integral. How are we doing? Is everybody on board there? Lots of students will get this wrong. Lots of students will make this x. Does everybody see why x is wrong? All right. And then let's see. Now let's talk about the upper bound. The upper bound. Come on. There we go. The upper bound. Let's see. This point, that curve, that equation. Again, I heavily emphasize this 4-step process. Identify the point. Identify the curve that it's on. Identify the equation of that curve that it's on. And again, the don't move too fast at the very end. Don't forget what you're solving for. We are in this equation solving for x. Okay, again, lucky break already solved for. Nothing to worry about in terms of, wait, is that a constant or is it a variable? It's just 1. And so this upper bound is 1. Yeah? Good deal. Okay, some harder ones. Suppose you have a domain. Now, I have to talk about language here a little bit. There's a term that's being used here. The domain is bounded by. We're going to come back and momentarily and talk about what we mean when we say a domain is bounded by some curves or, eventually surfaces, something like that. So first of all, let's draw these curves here. We have y equals x squared. Whoops. And we have y equals 4, which is that. So what do we mean if we say that the domain is bounded by those curves? This means two things. When we say bounded by, on the one hand, I mean that the D that I'm trying to define, its boundary consists of these curves. Here's the problem with thinking of that alone. This region over here, its boundary is only those two curves. That's not the one I'm talking about. Right? Ditto this region in here. Ditto this region over here. There's lots of regions whose boundary are these two curves. This phrase, bounded by, means more than that. Bounded by means not only is the boundary only these curves, it furthermore means that the region is bounded, that you can draw, you can put a fence around it, you can put it in a box. It doesn't run off to infinity in any different direction. Right? So there is only one region on this plane that is actually containable, that doesn't move off to infinity. And that's this region here. So this is what we mean by this phrase, bounded by. Is everybody with me? Are you willing to buy it? Okay. Cool. All right. So there's our region, and we're going to slice this. Oh, same deal where I've got a double integral given. Why are we interested in this double integral? Let's not worry about it. It's some application, whatever. We're only going to think about phase 2. We're going to turn double integral into iterated integral. Just phase 2, all we're going to talk about here. Let's slice it in this order arbitrarily. I've got, let's see, what's my range of values of x? Well, x, there's my first x slice, there's my last x slice, and notice the statement of the question doesn't give them. It doesn't really quite jump off the page at us. Right, so here we are going to have to do a little bit of work. This is what you got to do sometimes. I'll notice, for example, that my lower bound is defined by this point. And that point is on this curve which has that equation. But that point is also on this curve which has that equation. So it arguably still kind of the same process that we did before. Points, curves, equations, solve. It's just that now there's a point that's on two curves that has therefore two equations, in the pair of which I need to solve for what I'm interested in. Is everybody with me? Okay. Again, really easy to lose track. Forget what you're solving for. Don't move too quickly and conclude that my x bound must be 4, because there it is. It's y is already solved for. It's 4, and then you write that down and you move on. Before you remember, I'm not interested in y. I'm solving for x. I'm looking for an x bound. So very dangerous little moment, right? Make sure you're solving for the correct thing that you're supposed to be solving for. So in this pair of algebra, right here, inside of here, I need to solve for x, not y. Now, it's not hard to do. If x squared is y and y is 4, that means x squared is 4. That means plus or minus 2 are my candidates. And then I look at my picture and realize, well, I'm clearly in the range where x is negative. And so it's got to be negative 2. How we doing? Everybody's happy? Okay. Okie dokie. So negative 2 to positive 2, you can make an analogous argument for, this point. It's interestingly on the exact same two curves with the exact same two equations. This time, though, we're just clearly looking for the positive value of x. Okay. All right. So now we fix a value of x. We look at just that x value. On that x value, we want to find the range of values of y. Okay, lower bound, this point. That curve, that equation, solve for y. Already solved for, you gotta love it. So x squared. And then upper bound, defined by that point on that curve with that equation, solve for y. Again, lucky break, it's already solved for. So my upper bound is 4. Cool. Let's do it again. Slicing the other direction. This one's a little weirder. Doing the slicing in the opposite direction. Range of values of y. Well, this one, the y values actually do kind of just jump off the page at you. There's your lowest y slice. There's your highest y slice. The lowest one is clearly where y is equal to 0. The highest one is clearly where y is equal to 4. It says so right there. I mean, I guess you could say we're solving for y. Anyway, easy argument that y goes from 0 to 4. Then we fix a value of y. There's our y slice. Let's talk about the range of values of x. Lower bound for x. That point, which is on this curve, which has this equation. And again, a lot of students will mess this up. A lot of students will be like, oh, okay, cool. So x squared then. And again, that's moving too fast and sloppy. We are not interested in solving for y here. We are trying to solve for x bounds. We're looking for our inner bounds. Our inner variable is x. I need to solve for x in that equation. And again, seeing as I'm looking for the negative of the two possible candidates, that x is the negative square root of y. Ready good? Okay. And then likewise for the upper bound, this point, this curve, that equation, again solving for x, this time because we are clearly in the positive x side of the axis, we get the positive square root. Okay. All right, so let's take stock for a quick moment. We have a question. We've done it two different ways. Which one do we like better? I have a preference between these two. They're both fine. They're both legal. But I want the one that's going to be the least amount of work, the least amount of effort. And frankly, I'm a little concerned about these square roots right here. Because keep in mind, I don't yet know what my integrand is. And if that integrand is weird, then when I compute this x integral, and don't forget, when you compute the x integral, y is treated as a constant, and so that those bounds, square root of y and negative square root of y, they're going to be part of this inside integral. They're therefore going to be part of my outside integrand. When I get around to doing the dy integral here, it's going to be square root of y is going to be all over the place. That can be bad, right? Again, depending on what f is and depending on how the algebra works out, I don't like having square roots running amok in my integrands. So I'm concerned about that. Whereas, by comparison, I'm not at all concerned about these. I mean, I guess technically I prefer constants to polynomials, but I definitely prefer polynomials to square roots. So all else being equal, I like this one and not so much that one. Yeah? Okay. So now let's try to figure out how can we avoid problems like this. What about this this question? Looking at the statement of the question, what could have allowed me to anticipate that this is the way to do the slicing. This is clearly the better way to do the slicing. Well, there's different schools of thought on this. I mean, my take is I want to look at this question and ask, what went wrong with this approach? Why is it that I ended up with square roots? And the problem was that I had to solve for x. Where these came from, they came from when I was solving for x. I had to solve, therefore, for what you might call the input variable in that equation, right? If you think of, we got this, x squared as a function of x, and x is the input, y is the output, as it's set up here. I had to solve for my input variable. I had to invert a function. That was the problem. And so try to slice in such a way, whichever variable is your input variable, you don't want to have to solve for it. Don't put that differential on the inside. Whichever variable is your input variable, and again, I'm thinking of x as being the input variable, put that on the outside, like I did here, thus resulting in the nice answer that I got there. Is that cool? This is not a law. If you're a masochist and you want to do it the hard way, I guess you can, but it's going to be a problem. And that's another way to say that. It's bad reasoning. Okay, here's another one. Triangle, defined by certain corners. There. So here's our triangle. I want to slice up this triangle. Triangles are pretty easy, pretty boring most of the time, but there is something weird that happens here. Let's do the slicing in this order. Notice that y goes from 0 to 1. Then we focus on a particular value of y. For that value of y, x then goes from that point on that curve, giving me this bound as just y, to this point on that curve, giving me this bound as 2 minus y. I skipped over some details there. Y'all can fill in those blanks. It's a good exercise. Give that a try. But anyway, the punchline, it works out really nicely, no problem. But if we had gone the other way, if we had done the differentials in this order, things get annoying. Thinking about my range of values of x, it's tempting to say x goes from 0 to 2. The problem is, my upper bound for y is going to be on that curve for a little while, but then it's going to be on this curve for the later while. So in order to deal with this, what I have to do is consider x going from 0 to 1, start a whole new integral where I have x then going from 1 to 2, and treat these separately. And notice that for the first one, let's see here, I'm making color choices, y, for these values of x, the upper bound for y is going to be defined by that curve, which gives me that upper bound for y. Whereas, by contrast, for these values of x, as x goes from 1 to 2, my upper bound for y is on that curve, which gives me this formula for y. So, we have to break up the integral into two separate integrals. It was just a triangle, didn't look dangerous. We weren't concerned, but if you're a little too fast and loose about how you choose to do your slicing, you'll end up having to compute two integrals instead of one integral. And again, this is a bad idea. Not only do you not want to do the extra work, but it's bad reasoning, it's bad decision making. It's just not good. Right? So again, how do you avoid this? And I have my own little personal hack for avoiding this. When you are doing your slicing, your outside slicing, let's go back up to the top. My y slicing. Notice that I started there, but mid-process of the slicing, I didn't slice through any corners. I end at a corner. I start at a couple of corners. That's all fine. But in the middle of my slicing process, I didn't hit any corners. Whereas, Down here, as I was doing my outside slicing, doing my X slicing, started a corner, no problem, but as I'm doing my slicing, I slice through a corner. The fact that I sliced through a corner there is why I have to break up my outside integral at that point 1 and deal with it separately on the left side and separately on the right side. So it's a real nice little punchline. Try not to slice through corners. Right? Just nice and simple and pithy. Just try to avoid slicing through corners. How we doing? Is everybody all right? Okay, we're out of time. We'll pick up there on Monday. Y'all have a good weekend. Oh, real quick about the exam. I am actually done with the scoring of the exam. I haven't had a chance yet. I'm moving as fast as I can, I promise. But I haven't had a chance to do the curve. I will have that done by the end of today. Guarantee. Yeah. See you later.